So, what kind of applications can we study or systems can we model? Any type of mechanical or material conveying applications. So, as I mentioned before, because we are resolving individual particle collisions, the models within Rocky support high fidelity capture of local and global behaviors of bulk materials. So, we can consider how does the aspect ratio or blockiness of the constituent materials affect the way that the bulk will naturally pack? What is the bulk density? A concept that's absolutely critical if we want to satisfy mass flow rate requirements, for example. We'll also need to handle the equivalent volume flow rate through the system. Also, as part of this, various different adhesion models support users by allowing us to consider both wet and dry materials. And there's also a strong control over the movement of the geometries or boundaries in the system. And so we can have geometries physically or explicitly moving within the domain, as you can see on screen with the vibratory conveyor, for example. Or we can use an alternative solution where the boundary will remain fixed, but any objects which interact with the boundary will still see the same relative motion. And the motions that we actually can prescribe are quite extensive, ranging from user-defined translational and rotational velocities, periodic movements or oscillations, to a full 6 degree of freedom free body motion. Now, based on this, we can extract a multitude of data from the macroscopic behavior of the bulk. How does it flow through the system? Does flow happen in the first case, for the case of a poor flowing sticky material, for example? We can look at particle velocities and path lines. Are flow rates satisfied? And what's the power required to drive the prescribed motion in the system? Any sort of feeding, screening, or sorting applications can also easily be handled within Ansys Rocky. Now, it's critical to understand here that these types of applications operate on the particle scale. So here, the particle size distributions and their shapes play a critical role in the design of these systems and how they operate. How any given bulk material will behave also through that process. So for us as the modelers, it's vital for those important characteristics of the system to be able to be represented. We need to accurately model the PSD and non-sphericity to the particle shape. So for solution quantities, if we look at the particle or flow perspective again, we can hit all the same points as we did in the last slide. But as I alluded to earlier on, we can also look at things more locally. So take the video in the top right, for example, looking at flow through a feeder with a rotary valve. We can identify various different flow structures, stagnant zones, mixing characteristics. And through any of these types of processes, we can identify the sorting or mixing efficiencies, particle residence times, or how a PSD will segregate or percolate through that process. If the surrounding structure is also of interest, we can extract wall loads or pressure distributions and even take that further and extract that bit of data for the purposes of coupling with a finite element solver. And again, for example, we can identify what is the power or torque required to drive motion. Okay, so along with using DEM to study behaviors of bulk solids, we can also use the solver to investigate how the presence and movement of material will affect the structure around it. And one of the key aspects of this perspective is the concept of wear modeling, abrasive or impact wear modeling. Now, there are essentially two approaches that we can take to get an understanding of how geometries or walls or liners will wear away. The first is the least computationally intensive method, which is to consider the impact and shear energies for impact and abrasive wear predictions, which is what we're seeing in that top right, or what we saw in that top right video. And we can use this to identify wear hotspots with the understanding that regions which will experience higher energy collisions will correspond to more volume lost by erosion. And so we can use these kinds of heat maps to identify those regions which are prone to wearing out. And we can extrapolate data and say, okay, there was this much energy consumed by abrasive collisions after, say, 30 seconds of steady state operation. We can then expect after an hour it will be closer to X joules. Now, the alternative method is to use the explicit geometry modification tool in Rocky or the explicit wear model. Now, this is an application of Achard's wear law, where the volume lost is correlated by the work done due to frictional forces. It's important to understand that when we are considering wear, obviously the timescales that this phenomenon operates on is in the order of hours, days, or months of continuous operation. And this is not something that we can feasibly model at a 1-to-1 ratio in our DEM models. We'll typically be running models with a simulation duration of maybe a few minutes tops. So what users can do is to effectively map a real life duration with an equivalent simulation duration, which is what we're seeing in this graphic here. And we can do this by modifying the simulation wear rate. So this is a user-defined model parameter which controls the proportion of volume removed per unit of applied shear energy. One of the other useful capabilities for investigating these types of systems is, of course, particle breakage modeling. So there are two formulations: the discrete formulation, where you can imagine this uses a particle with a fixed mesh. Basically, it's comprised of a certain amount of elements which can break apart depending on tensile or shear stress criteria. So the fragment size distribution is almost predefined based on the way that particle is meshed, essentially. Now, the alternative is the instantaneous formulation, which is applicable to faceted particles like the polyhedron that you see on screen. This breaks apart into a number of fragments with varying size depending on the collision energy and the location of the collision relative to the particle. So these models have been validated, preserve both mass and volume, and we can use this to predict the progeny size distribution, the mass flow of material through crushing processes, for example, and of course identify any zones within the domain which are prone to breakage and understand how that material breakdown will affect flow characteristics. So I've got a nice case study here. This was some work done by Conveyor Dynamics, who had an existing chute design. And what was happening with this was that at certain flow rates, the chute was plugging. And they were able to replicate this behavior in Rocky. So starting off by identifying some potential problems with the flow, but importantly, we can see that blockage effect has been captured. So looking at belt wear from a shear and impact energy perspective, identifying the power required to drive the belt on the receiving conveyor. And now with this information that they had gathered with their first model, they were then able to propose a new and improved design to address those challenges that they had identified initially.